So I'm going to talk about soft embedded FPGA fabrics and how to do top-down physical design for soft embedded FPGA fabrics and demonstrate a few applications of soft embedded FPGA fabrics using our tape outs. So as you're all probably familiar, most modern devices, starting from small embedded systems to high-end mobile phones, are built using system-on-chips. System-on-chips typically contain one or more CPUs, some fixed function accelerators, and some I/O peripherals for interfacing with the memory and external world. And due to its ubiquitous use across multiple application domains, there is an increasing need for adding extensibility and flexibility to the SoCs while improving efficiency. Reconfigurable logic is an excellent solution to this problem. While reconfigurable logic has been around for decades in the form of FPGAs, they are primarily available as discrete ICs. But discrete ICs increase the cost, have limited bandwidth, and use power-hungry IOs. Hence, they are not a great fit to use with SoCs. The solution to this problem is to just take the FPGA fabric and embed it inside the SoC. This provides low power, high bandwidth interface to the SoC and also reduces system cost. So this approach naturally has been gaining popularity over the last decade. Many existing FPGA companies and new startups such as FlexLogic, QuickLogic, etc., are offering eFPGA IPs for inclusion into SoCs. Naturally, how to design and use eFPGAs in SoC is becoming an active area of research. So eFPGAs are used in two ways. Primarily used in two ways. One as an accelerator to accelerate CPU workloads, or as glue logic to interface with external components, sensors, memories, etc. They are also very useful for feature addition, bug fixes, and security in the context of SoC. So there are two types of eFPGA fabrics, hard and soft. Hard fabrics are built using manual custom layout techniques to maximize density, performance, and energy efficiency. But as technology scales down to single-digit nanometers, layout design rules are becoming increasingly complex, and manual layout is slow and requires a lot of time and effort. Soft FPGA fabrics, on the other hand, are implemented using standard cells and automatic place and route tools. So this ensures excellent process portability and enables agile implementation of the fabric. And you can turn around from architecture spec to layout within 1 to 2 days. But the physical implementation of FPGA fabrics using traditional ASIC EDA tools is not straightforward like other blocks on the SoC. This is primarily due to the complex interconnected nature of the routing fabric in the FPGA. So in this work, we propose a new methodology to simplify the physical implementation of eFPGA fabrics and also demonstrate some novel applications of soft eFPGA fabrics using our methodology. So a quick outline. First, I'll cover some background and related work on eFPGAs and how they're used in SoCs. Then I'll talk about our top-down methodology and cover two proof of concept test chips that we fabricated. Later, I'll talk about two applications. One is hardware redaction for protecting sensitive IP, and the other one is using a soft eFPGA as a reconfigurable RISC-V Co-processor. Finally, I'll summarize and conclude. So let's start with related work. eFPGA fabrics are most commonly used in SoCs as either accelerator or glue logic. The sizes of eFPGA fabrics used in in the literature vary from 100 to about 9K LUTs. And there are different types of fabrics to cater to the low power and high performance application requirements. So let's look at a few examples. The first is a SIMV SoC from ARM and Harvard, I think. So this SoC uses a FlexLogic eFPGA with about 9K LUTs and 80 DSP tiles. The eFPGA hangs on the system interconnect bus and occupies around 4 mm² on a 60 nanometer FinFET process. This eFPGA is primarily used to accelerate DSP and crypto applications running on the A53 dual-core CPU. The paper shows significant throughput and energy gains when using eFPGA for acceleration. So the second example is the Arnold SoC. This is from EPFL, and it's a relatively low power SoC meant for IoT edge nodes where static power is a major concern. This SoC uses a commercial QuickLogic eFPGA with about 6K LUTs and 2 MAC units. The eFPGA is used primarily as used as both glue logic and accelerator in this case, and it is primarily used to interface with non-standard IO peripherals and sensors. And for the accelerator use case, they are using it as a accelerator to accelerate a binary neural network running on the RISC-V processor. So in the third example, we will look at a smart power SoC from ST Microelectronics. This SoC uses a tiny in-house eFPGA with about 96 LUT4s. The fabric uses a multi-stage switching architecture to facilitate easy synthesis. In this SoC, the eFPGA is used as glue logic to offload IO tasks that consume CPU cycles. By offloading the IO tasks to the FPGA, you can greatly improve the efficiency of CPU as it can be put to sleep while eFPGA takes care of the IO tasks. And finally, another example is the Dragonfly SoC from Sandia Labs. In this SoC, the eFPGA basically glues the two cores and the IO and memory interfaces together. This SoC also uses a FlexLogic eFPGA with about 4K LUTs to implement various glue logic and acceleration functions. So to summarize, there are a number of recent SoC designs that use eFPGA Fabric in various ways, depending on their power and performance requirements. And most of these designs rely on commercial hard IP-based FPGAs. But eFPGAs can also be built as soft IP from RTL. Soft and hard eFPGAs have different advantages and disadvantages. Let's look at a quick comparison. So hard IP-based fabrics are delivered as layout and ready for integration into the SoC, as we saw in the previous examples. Hard eFPGA fabrics are designed using custom and semi-custom techniques. They require very high design effort and suffer from poor process portability. If you want to make any change to the process or to the FPGA architecture, it will require a lot of redesign. Hard IP-based fabrics can be used to, hard IP can also be used hard IP-based fabrics can also be designed using standard cells, and examples of that include FlexLogic and QuickLogic eFPGAs. Using standard cells helps with reducing the design effort, and it still suffers from poor process portability. For example, FlexLogic and QuickLogic require about 3 months to 6 months to port their existing eFPGAs to new process nodes. Soft eFPGA fabrics, on the other hand, are defined using RTL, and they do not need any custom layout. They can be easily ported to any process technology with a standard cell library. Moreover, if you want to change the architecture, it's just a change in the RTL, and you just run through the physical design flow, and basically you get quick turnaround times, and it increases the productivity greatly. While soft eFPGA fabrics offer some advantages in terms of productivity, flexibility, and portability, they are not straightforward to design. Let's look at some of the major design challenges for implementing a soft eFPGA. The first problem is that the FPGA fabric is highly interconnected, and it has thousands of combinational loops, as shown in the figure. I've just illustrated a few, but you can imagine like there are all sorts of combination loops that can be formed between logic blocks and the switch blocks. Typical ASIC designs do not have such combinational loops, and ASIC EDA tools cannot optimize designs with cycles in their timing graph. In the eFPGA fabric, there are two kinds of loops. One is the intra-tile loops and the inter-tile loops. The intra-tile loops exist inside of a tile, basically a loop between the local interconnect and the LUTs inside of a tile, and they can be broken easily. But intertile loops can span multiple tiles and are hard to break. The second problem is related to timing path explosion. We can break the intertile loops by disabling, say, one of the turns in the FPGA routing fabric, say the left turns, to eliminate cycle formation. But even after breaking the loops, you will end up with thousands of paths between different logic blocks meandering all over the FPGA fabric, as shown in the figure. I showed a few paths from the green logic block to the red logic block, but from every other logic block, you will have multiple such paths meandering all over the FPGA with different path lengths. When you have these meandering paths, it's very difficult for the ASIC tool to optimize this because the path length varies greatly and you cannot put a single clock delay constraint for optimization. Therefore, it's very difficult to constrain these and optimize these properly using EDA tools. The third challenge is to provide regularity in delay across the FPGA fabric. So the FPGA CAD tools assume a delay regularity for timing-driven placement and routing algorithms, and it is important to retain this property in the soft FPGA fabric. There are a few other challenges, such as configuration, clocking, compatibility with automatic test pattern generation tools. They need some work, but they can be implemented. There is some challenge in implementing those, but they can be overcome. So now that we know the various design challenges, let's look at how existing soft FPGA methodologies solve these design challenges. Prior literature published over the last decade take two different paths to dealing with this problem. The first path is to modify the routing architecture to eliminate the intertile loops altogether. The second path is to use a bottom-up approach where each tile is synthesized in isolation to avoid the intertile loops and then stitched together to form the entire FPGA fabric. So one approach to interconnect modification is to use a directional architecture where signals flow from left to right, but obviously this trades off interconnect flexibility for synthesizability. The second approach is to use a multi-stage switching network or a hierarchical tree-based architecture to avoid the loops. Another third approach presented in literature is to use a cycle-free switchbox design to eliminate intertile loops, which is used by the Princeton reconfigurable gate array approach. But the problem with these approaches is that they cannot be used to implement and study the most used island-style FPGA fabrics. Moreover, any changes to architecture may require special support for FPGA CAD tool flows. So in our work, we basically focus on island-style FPGAs supported by VPR, where you can describe any type of island-style routing architecture in VPR. So another alternative approach to synthesize FPGA fabrics without any architectural modifications is to use a bottom-up method. So here, each tile in the FPGA fabric is synthesized separately to avoid intertile loops, and then you can stitch them together to form the larger FPGA fabric. This method has been used by multiple publications over the past decade, including the recently published OpenFPGA framework. Since each tile in the bottom methodology is optimized in isolation, there is no global timing view spanning multiple tiles to optimize the channel wires, basically, which span multiple tiles. To mitigate this problem, prior works using bottom-up approach rely on enforcing a strict floor planning requirement and also employing a customized manual buffering strategy where they account for the wire lengths in a given process and like buffer them properly and make sure that all tiles are spaced evenly so that you can replicate them. So it requires a lot of manual effort. But bottom-up methodology comes with its own set of challenges, as you were saying. The first is the fabric customization is time-consuming because if you're going to change the architecture and your tile size changes, then you have to rework your floor plan and the buffering strategy. Secondly, if your technology changes, you have to redo all this work. Moving from a 28 nanometer to like a 7 nanometer will take a lot of time, will take some time and effort to floor plan and devise a good buffering strategy. Therefore, bottom-up approaches basically introduce significant deviations to the standard push-button ASIC flows, where you just take an RTL and pass it through the flow, and you have a layout. So to address this issue and simplify our design flow, we propose a top-down methodology for implementing soft FPGA fabrics. So I'll talk about the top-down methodology in this section. So the goal of the top-down methodology is to eliminate the need for manual floor planning and buffering and enable a flat one-shot implementation. To achieve this, we create a global timing view of the fabric for the EDA tools. How do we do this? We do this by enabling by modifying the switch box mux. The switch block mux basically receives inputs from the CLB as shown in blue, and also inputs from the channels shown in green. So what we do is we take the switch box mux and group the channel inputs and the CLB inputs separately and disable all the timing arcs through the channels. So this basically breaks all of the intertile loops. But the timing paths through the CLB inputs are still active, and hence all the channel wires in the FPGA fabric is basically optimized by the EDA tool. So we use this. We also use location agnostic clustering of switchbox muxes to minimize the delay on the turns, because on the switchbox turns, we are essentially breaking the timing paths. So this is our approach to deal with creating a global timing view for the eFPGA fabric. So some of the advantages of this methodology, since it's compatible with standard ASIC flows, it can be easily ported to any process with the standard cell library. We have used our methodology to tape out FPGAs in multiple process nodes, including the 16 nanometer FinFET node. So I'll quickly talk about our design flow, fabric generation flow. Our fabric generation flow relies on two tools, Chisel hardware construction language from Berkeley and the VPR tool from University of Toronto. Our fabric generator reads in the VPR routing resource graph that describes the FPGA fabric, and then it generates a RTL with the modified switchbox muxes required for implementing the top-down methodology. It also dumps loop breaking, timing exceptions, and as STA constraints for optimization by ASIC EDA tools. So once you have the Verilog and the STA constraints from a generator, you can take it and run it through the physical design tools, using the standard EDA flow, standard ASIC flow. So I'll quickly skip this slide. It just shows the various hierarchies in the Verilog that we generate. Not that important. Then for configuration of for the configuration cells, you can either use latches organized as a memory or flops organized as scan chains. Latches offer a small area advantage, but the important drawback is that they are not readily compatible with automated ATPG tools. We chose to go with the scan-based approach because it's very simple to implement. It can be extended to support a wide range of features such as scrubbing, live reconfiguration, etc. And most importantly, it's compatible with ATPG tools. So when you include an eFPGA, your standard ASIC flow, which takes care of DFT and ATPG, will work with our approach. And this is very important for SoC integration, because if you want to put something into production, you want to make sure that it is compatible with standard test practices. So in order to use our eFPGA, we have like custom bitstream generator, which you can use for formal and functional verification of the RTL and the mapped application. Once the verification is complete and you're satisfied, then you move on to the synthesis and place and route. So for the backend flow, I will run through an example of a 10x10 fabric described using VPR, and I'll basically run through each of the place and route steps and show you how it can be placed and routed. So for this example, I'll use a logic block which is composed of 8 4-input LUTs and a routing fabric with 80 channels with both L2 and L4 wire segments. And this fabric is described in BPR. And we use our fabric generator to basically dump the RTL and the timing constraints required for physical design. So let's take a quick look at the constraints. The first section defines the two clocks. One is the logic block clock, where the flops of the logic blocks are, this is the clock used to clock the flops in the logic block. And the second is the configuration scan chain, where you load the bit stream. The second section specifies the loop break exceptions, which break the intratile and intertile loops in accordance to our top-down methodology. And the last section sets the path delay constraints for the L0, L2, and L4 paths in the fabric. So this constraint is used by the tool to optimize the channel wires. Okay. So once we have the RTL and timing constraints, we can run logic synthesis. Synthesis takes around 8 hours for 10x10 fabric and results in about 0.3 million instances with an area of about 0.25 mm². So after synthesis, the next step is basically floor planning and placement. Here, we don't need to do any explicit floor planning. So all we do is allocate the given area required for the block and then place the IOs. So after that, we perform timing-driven placement. You can see the result of the placement on the right. 10x10 logic block array. You can see the logic blocks highlighted in blue. It's an array of 10x10 logic blocks, and you can also see the routing muxes are automatically placed in their corresponding locations without any explicit placement constraints or floor planning of the tiles. Okay, so after placement, the next step is clock tree synthesis. The ASIC tools basically take care of this, and they're able to synthesize the clock tree with very little skew, less than 100 picoseconds. So after the clock tree is built, you basically go and fix the hold violations, which is also taken care of taken care by the EDA tools automatically. The next step is to route the design and run post-route optimization to fix any leftover timing violations. On the right, you can see the congestion maps for different routing layers. Blue and green spots in the congestion map indicate that the density of the routes is low and there are many unused tracks. From the figure, you can see that the standard cell-based FPGA is not routing limited, and there is ample area to add more channels or increase channel width if necessary. So the table on the right shows the area utilization and runtime for the 10x10 fabric. The area utilization increases by about 5% through the physical design process, and most of it is due to buffers created for CTS, the clock tree, and the whole fixing post clock tree synthesis. The total runtime is about 12 hours, as you can see. PNR runs in 3 hours, and then synthesis takes about 8 hours. This is slightly on the higher side. Typically, synthesis takes lower time. There are some small issues with the synthesis tools dealing with combinational loops. So we are currently working to get that to under 3 hours, and we have found some workarounds to get that to under 3 hours. So essentially, if you want to place and route, synthesize and place and route a 10x10 fabric in like a 60 nanometer process, it would take you less than 6 hours with the fixes. Okay, so after we have done place and route, now let's look at the path delay histograms. These give us an idea of how well the EDA tools optimized each of the paths. As you can see, the standard deviation is less than 3% for all the L0, L2, and L4 paths in the FPGA, which shows that the tool did a really good job of maintaining equal timing across the FPGA fabric. So next, we show the variation in the path delays across different stages of the L0, L2, and L4. So if you take a L4 path, it starts at a CLB, goes to a switch box, then there is a length 4 wire, then there is this connection block, and it goes to the another logic block. So you can see that the tool did a reasonable job of keeping the delay variation low across the various stages. Moreover, you can see these incremental delays of each of these stages, and you can use these incremental delay values to annotate timing information back to the VPR architecture file. So these plots kind of show that you can back annotate the values to VPR, and the tool does a good job at keeping the delay variations low. Okay, so far we have analyzed the path delays which we have explicitly constrained, basically the L0, L2, and L4 paths. If you remember, for the turns, we were using location agnostic clustering, and we were breaking the timing paths through those turns. So now let's look at the delay variation of these turns. You can notice two things. First is the delay variation is larger, basically because it's not explicitly constrained. Second is the delay variation has multiple modes. So this is due to the varying size of switch boxes across the fabric. Not all switch boxes are identical. Some switch boxes have 5 inputs, some have 13 inputs, some have 16 inputs, etc. So the number of mux stages varies, and this is what is showing up as modes in the delay distribution. VPR has a nice feature to model this multimodal switch block delay. In fact, we can use VPR delay model to specify separate delays for L2 and L4 muxes of various sizes, as shown in the figure. So by making a small edit to the RTL in the switch block, we can explicitly specify these delays to match the VPR timing spec. So to demonstrate this, we split the switch blocks into small and large switch blocks, and we separately specify delay constraints for each of those as shown in this listing. So once you specify that, the tool actually can see the paths through the turns and optimize them according to the delay spec provided in the VPR architecture file. So here you can see the delay variation plots before and after optimization. So once you specify these constraints, you can see that the delay variation is significantly reduced. And you can see that we can give two different delays for the small switch blocks in orange and the large switch blocks shown in green. So this concludes the backend delay analysis. Here we showed that we can achieve good evenly matched timing across the entire FPGA fabric, and we can specify timing constraint and let the tool do all the work to optimize the different paths for our given timing constraint. So now that we have went through the backend flow, let's look at how top-down compares with bottom-up. So to compare with bottom-up, we implement two FPGA fabrics. We implement a 6x6 eFPGA fabric using the top-down and bottom-up methodology. The routing fabric has about 80 channels, and we use length 4 wires in this architecture. The VPR architecture parameters used are shown in the table. And all these experimental results are based on post-layout implementation. Since the goal of the top-down methodology is to eliminate the need for floor planning and manual buffering, we implement two versions of the design, with and without floor planning. For the design with floor planning, we explicitly specify the placement location of each of the tile. For the design without floor planning, we let the timing tools, timing tool basically dictate the placement. So the constraints and the connectivity basically dictate the placement. So after placing and routing the fabric, we analyze the performance of various benchmark designs in top-down and bottom-up fabric. We find that the top-down performance is similar to the bottom-up performance with and without floor planning. The top-down designs also perform better than bottom-up designs with floor planning. And one other thing we see that the buffering is the buffering strategy is really important. If you have a poor buffering strategy, then you have a large delay. But if you have an optimized buffering strategy, then you can reduce the delays. Another thing we can see is that the delay histograms for the top-down shown in red show minimal delay variance, but the delay histograms for the bottom-up methodology show a large delay variance, basically due to the lack of global timing view with spanning multiple tiles. So to summarize, top-down designs can achieve similar or better performance to bottom-up designs without the need for manual buffering and floor planning approaches, which basically improves productivity. Okay, so in this section, let's look at some of the test chip results. Let me just check the time. Okay. So to validate our top-down methodology, we fabricated proof of concept soft eFPGA test chips. In this one, we have a 16x16 tile eFPGA with about 2K 6 input LUTs. The eFPGA occupies a core area of 1.7 mm squared, and you can see the measurement setup and the layout screenshot in the image. So the figure on the right shows the area and delay breakdown of the eFPGA test chip. About 8% of the area is occupied by the LUTs and flops, 50% is routing muxes, 33% is about 32% is the configuration cells. There are like 0.3 million configuration flip-flops for this FPGA. And 10% is due to various hole buffers and CTS buffers and timing violation fixing buffers. So as for the delay breakdown, the LUT and flop delay account for about 33%, and the remaining 2/3, 67%, is due to the routing muxes. So the routing muxes are basically the switch box, connection box, and the crossbar plus the wire delays. So we evaluate the performance of the soft eFPGA fabric by implementing 4 different designs, including AES, a soft multiplier, a pipelined S-box, and a SOBEL filter. The standard cell-based eFPGA can operate over a wide operating range from 0.4 to 1 volt because we are not using SRAM for configuration storage. And it also, the leakage power is also very low, 500 microwatt at 1 volt. And it can go down to as low as 160 microwatt at 0.4 volts. We can run AES at about 200 megahertz. And then if you pipeline the designs, then you can run at up to 630 megahertz. On the right, you can see this SHMU plot of the AES S-box showing operating speeds up to 630 megahertz. Okay, so to compare the performance of the eFPGA with some of the commercial ones, if you see the performance, it's about the same as a 28 nanometer zinc FPGA and is about 2 to 3x lower depending on the application compared to a 16 nanometer Kintex FPGA. This difference is primarily due to the highly optimized custom layout used in commercial FPGAs, but there are also other factors contributing to the increased delay, like lack of architecture features such as carry chains, direct connections, and some of the inefficiencies associated with the open source tool flows using YOSYS for synthesis and then VPR. So now that we have discussed the 16 nanometer test chip, let's move on to the 22 nanometer test chip. So our 22 nanometer test chip implements a heterogeneous fabric. As you're all aware, heterogeneity introduces a lot of complexity, especially for the bottom-up approach. For example, a fabric with DSP and DRAM, you must implement 27 different unique tiles if you're using the bottom-up approach. Moreover, tile size irregularity also complicates the manual buffering approach. In this case, our top-down methodology can simplify the design by allowing a flat one-shot implementation of our fabric. Our fabric generator supports custom tiles in the form of hard macros, soft macros, or basically RTL. So to demonstrate this capability, we implemented a 12x12 heterogeneous soft eFPGA with BRAMs as hard macros, CLB as soft macros, and DSP as Verilog RTL. So all of these were put together in the same fabric, and we implemented it in a 20 nanometer FinFET process. On the right, you can see the VPR architecture along with the corresponding physical layout. So using the top-down methodology basically enabled us to generate multiple fabrics to trade off power, performance, and area metrics very easily. Modern processors offer multiple standard cell libraries for power performance area trade-off. For example, the 22nm process we use offers seven different VTs for standard cells. It offers high performance standard cells with 7-track height and compact standard cells with 6-track height. And it also offers thick gate cells for ultra low leakage. So just by changing your standard cell library, you can create different fabrics with different performance constraints, like high performance or low leakage fabrics can be easily fabricated using the same design methodology without any additional effort. To demonstrate this, we implemented a high performance and low leakage version of the same 12x12 heterogeneous fabric. The high performance version uses a combination of LVT, SVT, and HVT cells, whereas the low leakage version uses HVT for logic and SVT for the clock tree. So the figure on the right shows the shmoo plots of the two fabrics implementing 16-bit vector multiplication using the BRAM and DSP blocks on the 12x12 eFPGA. The high performance and low leakage fabrics can operate up to 560 megahertz and 375 megahertz at 0.95 volts. The low leakage fabric operates 33% slower compared to the high performance version, but the leakage is about 6x lower. So our proof of concept homogeneous and heterogeneous test chips show that top-down methodology works as expected in silicon and is well suited for design of agile design of soft eFPGA fabrics. So now I will talk about two different applications that we implemented using our methodology. The first is hardware redaction for protecting sensitive IP. To quickly motivate the need, number of leading edge fab houses have been on a steady decline over the past decade in US due to the exorbitant costs required to keep up with technology scaling. Moreover, the fab center of mass has been shifting towards Asia, and almost 3/4 of the fab capacity is in Asia. Therefore, increasing number of customers, which include industries and governments, have to rely on third-party fabs. And reliance on third-party fabs raises a number of security concerns for manufacturing sensitive IP. Some of the threats include netlist extraction, IP privacy, Trojan insertion, overprotection, etc. So to deal with these threats, countermeasures such as logic locking and obfuscation have been proposed in literature. Locking techniques basically intend to prevent unauthorized use of the critical IP, but they do not hide the design intent of that particular IP. Obfuscation techniques, on the other hand, partially hide the design intent, but they do not completely conceal the critical IP. In this work, we propose for this application, we propose an alternate method called hardware redaction, which is used to completely conceal the critical IP from the foundry. It is analogous to how intelligence agencies redact information from a sensitive document. Redaction basically completely removes the sensitive IP and replaces it with reconfigurable logic. In this case, we use a soft eFPGA using our top-down design methodology, as it's compatible with standard ASIC flow and can be easily integrated into other designs. So one important point to note here is that the idea of using fabrics for FPGA fabrics for obfuscation is not new, but there are several practical challenges for using FPGA fabrics for redaction. Prior work that looked at this relies on commercial eFPGA hard IP, or they have their own custom designed fabrics. Both these approaches have some important drawbacks. If you're using eFPGA hard IP from commercial vendors, they typically contain thousands of LUTs. Therefore, it is not very suitable for fine-grained redaction, where you might need small fabrics with different configurations of routing tracks and LUT sizes. Moreover, hard IPs may not be available across a variety of process nodes, limiting usability. Using custom fabrics can result in low VLSI overheads, but they require custom semi-custom layout, which is highly time consuming and also suffers from poor process portability. Therefore, this approach is not compatible with typical SoC design schedules, budgets, and fab diversity requirements. So to overcome these drawbacks, we propose the use of soft eFPGA fabric for redaction, and we provide a tool flow along with it for realizing this in silicon. So the input to our tool flow is basically a marked RTL with the critical IP. Our fabric generator takes in the critical IP and maps it to a eFPGA fabric, the smallest possible eFPGA fabric by using VPR. It then spits out the redacted design in which the critical IP is completely removed and replaced with the RTL of the soft eFPGA fabric. Our flow also generates the timing constraints required to ensure compatibility with standard ASIC flow. Therefore, we overcome the major disadvantages associated with using hard IP or a custom fabric. Another advantage is that since we are using a soft eFPGA, we can mix the ASIC RTL and eFPGA RTL to optimize our design further. If you consider the eFPGA fabric, several designs can be mapped onto the fabric. Since we do not know the design beforehand, all the routing resources in the eFPGA fabric have to be optimized evenly. But for redaction, this is not the case. Here, we already know the design that we're going to implement on the fabric. So we can optimize the eFPGA routing fabric for this specific design, and we can improve the performance compared to a generic fabric. So we use two modules for demonstrating this. One is the GPS module from MIT Common Evaluation Platform, where they have a list of critical IP that you need to redact. And the second design is we use a 5-stage RISC-V core, and we redact the control logic of the RISC-V. Because we redact the control logic because this is a small portion of the CPU, but redacting it renders the entire CPU unusable. So now let's look at some of the post layout results. So for the GPS design, once again, yeah. For the GPS design, the eFPGA generic version has about a 3x delay overhead compared to the eFPGA, but the eFPGA opt version shown in green does not have any delay overhead. The opt version was able to reduce the delay overhead as the redacted logic was not in the critical path. Both the designs incur about 1.4x overhead in terms of power and area. For the RISC-V core, the eFPGA generic has a 5x delay overhead, and it reduces to 2.3x for the eFPGA opt version shown in green. The delay overhead does not reduce further because the control logic is actually in the critical path of the design. The power and area overheads for the redacted versions are about 2 and 1.7x respectively. So we taped out a test chip using a 20 nanometer FinFET process that contained the original and redacted version of the eFPGA generic redacted version of the RISC-V core. So the original design operated at about 1.3 gigahertz, whereas the redacted version operated at 300 megahertz. And the measured performance on silicon was in line with the post layout delay estimates reported in the previous slide. In addition to that, Cadence Design Systems evaluated our soft eFPGA redaction in their production EDA flow, and they used it to tape out an SoC with the redacted GPS design. Now, let's move on to the next application, which is the RISC-V Co-processor. This is more of a work in progress. Here, we will discuss how we integrated the soft eFPGA fabric into the RISC-V SoC and present some preliminary results. So we have seen previous examples of SoCs where the eFPGA fabric sits in the main system bus. And this approach results in high latency to communicate with the CPU. So if the eFPGA was implemented as a co-processor along with the CPU, then we can get the advantages of low latency to communicate with the CPU and also access to the CPU cache. So in this work, we decided to go with the co-processor approach. One example of prior work in this area is the addition of soft eFPGA to the extensor processor. This work used a custom eFPGA with about 3K LUTs, and it uses a hierarchical routing architecture for the eFPGA. The design was targeted at accelerating image and voice processing applications, and it demonstrated about 2 to 10x speed up depending on the application. The main challenge with eFPGA and CPU integration is synchronization. The eFPGA can operate at multiple frequencies depending on what application you're mapping onto the eFPGA, but then the CPU works at its fixed clock. So in order to deal with this, extents are used a specific clock stretching approach. They stretch the CPU clock based on the instructions executed on the eFPGA. This approach is not only complicated, but it's difficult to implement and verify. So in our work, we used a simplified approach using RISC-V. RISC-V provides a Rocket coprocessor interface to connect coprocessors, and the ISA also provides custom instructions for executing your specific tasks. So the CPU and eFPGA in our design operate on two separate clocks, and we use asynchronous queues for communication. This way, we can simplify the integration by decoupling the application clocking from the SoC and CPU clocks. Therefore, it comes with a small cost in latency introduced due to the asynchronous queues. Okay, so the figure on the right shows the block diagram of our SoC. We generated the SoC using a chipyard, the chipyard infrastructure developed by Berkeley. The SoC has a 64-bit Rocket core with 16 kilobyte L1 cache and 512 kilobyte L2 cache. The core can operate at around 500 megahertz. And the FPGA is connected to the RISC-V core using the ROCC interface, and it's also connected to the GPIOs. This SoC was designed by two students, myself and one other collaborator, Oz Atley, and it took us about 5 to 6 months to design the SoC from RTL to tape out. Mainly thanks to Chipyard for making this SoC design possible in such a short time. Now let's look at the eFPGA used in the Fabric. eFPGA used in the SoC. The Fabric is composed of 6 14x14 heterogeneous eFPGAs with about 500 IOs. The eFPGAs have a total of 4.3K fracturable LUT5s, 30 BRAMs and DSP blocks. The eFPGA occupies about 4 mm squared. We added a few features compared to the previous version. One feature is the ability to reconfigure during operation using shadow latches. Another feature is to implement fracturable LUTs to improve performance. On the right, you see the layout of the Fabric implemented using our top-down methodology. The CLBs are highlighted in pink. The DSP blocks are highlighted in gray in the middle, and then you can see the VRAMs in brown just to the right of the center. Okay, so we recently received this test chip back, and we are in the middle of the bring up. This was our first attempt at designing an SoC, and I'm delighted that most of the functionality worked as expected. The RISC-V CPU runs at about 500 megahertz, and we verified that the ROCC interface works with some basic tests. As an example, we created a custom instruction on the eFPGA to implement pop count, which is not yet readily available in the RISC-V ISA. And the test results show that we can achieve around 10x speed up on the pop count instruction, custom pop count instruction, where with the RISC-V running at 500 megahertz and the eFPGA running at around 100 megahertz. The SoC platform is up and running, and we hope to develop and demonstrate more applications in the future. So to conclude, we presented a top-down design methodology, which is compatible with standard ASIC flow, which can greatly improve the productivity of implementing soft eFPGA fabrics. It is portable across multiple process nodes without any modification, and it can enable agile design of heterogeneous eFPGA fabrics within a few hours to a day. So we also demonstrated proof of concept test chips to validate our methodology, and we showed that we can intermix ASIC and eFPGA RTL together and demonstrate novel applications with the soft eFPGA approach.